Hello everyone. Today we will see the last topic in this chapter, forced oscillations and resonance. The highlights of this class, we will see the theory associated with forced oscillations, which is also called driven oscillations, and we will see the conditions under which the oscillations will exhibit a phenomenon which we call resonance. So forced or driven oscillations, if you look at the damped oscillations, you can see, as we have seen already, when there is damping which is present, the amplitude of the oscillations will keep on decreasing. So if you apply a periodic force so as to prevent the oscillations from dying out, we will be able to maintain oscillations without any decrease in amplitude. As you can see in this diagram, if you apply a periodic force, constant periodic force, we will be able to maintain the oscillations without and we will be able to prevent it from dying out. So we will see the theory of forced oscillations. Let us say we apply a periodic force which is given by F0 sine pt, where F0 is the amplitude and P is the angular frequency of the driving force. This F is the driving force which is given by F0 sine pt. The system is undergoing oscillation, so therefore other forces are also present in the system. Let us assume that as we had seen earlier, there is damping force which is given by negative gamma dx by dt, and since it is oscillations, there will be restraining force also which is given by negative kx. Gamma is the damping coefficient and k is the spring constant. So therefore the equation of motion of that system which is undergoing oscillations with in the presence of damping, and also when an external periodic force is applied, it can be written like this: m into d square x by dt square equal to negative gamma dx by dt minus kx plus f0 sine pt. So we can rearrange the terms, divide throughout by m, and you will be getting this equation. So we can write down from the previous sections, we know that gamma by m can be written as 2k, where k is the damping constant, and this capital K by m is omega 0 square, where omega 0 is the natural frequency, and we put this f0 by m as small f0. So we can express the equation conveniently like this. This represents the equation of motion of a driven harmonic oscillator or forced harmonic oscillator. Now how we will solve this equation? This is our equation for a driven harmonic oscillator. What we do is see, this is as evident, this is a second order differential equation in x. Okay, x is the displacement, instantaneous displacement. So we will put x equal to a sine pt minus theta, or we will assume a solution of this form: a sine pt minus theta. So we can naturally, what we have to do is, this is what I right now said: x is equal to a sine pt minus theta. You have got dx by dt and d square x by dt square. So from this equation we find out x dot, which is dx by dt, and x double dot, which is d square x by dt square, and we will put it in this equation. So this is what you are going to get when you do that. Then see the differentiation: first order differentiation, second order differentiation. This is what we get. So we substitute it in the equation, this equation, and then we do one modification on the right hand side. The argument of the sine function, which is sine pt, will just add and subtract theta, so that on the right side we have got a sine a plus b, which we can write as sine a cos b plus cos a sine b. Then what we will be having is, on both left hand side and right hand side, we will be having terms like sine pt minus theta and cos pt minus theta. So if this equation is to be satisfied, the coefficients of sine pt minus theta and cos pt minus theta on either side should be equal. So when we do that, you get this, you get one equation like this: A omega, you equate the coefficients of sine pt minus theta and cos pt minus theta separately on either side. So you'll be getting two equations. So this is what you are going to get: a omega 0 square minus p square equal to f0 cos theta, and 2k ap equal to f0 sine theta. So you can solve this equation because you have got cos theta and sine theta here. So if you square and add, you will be able to get rid of the sine theta and cos theta. So then you will be able to solve it for a. So then that is what is given here. A is equal to, you will obtain a as f0 divided by root of omega 0 square minus p square the whole square plus 4k square p square. Then this value again you can if you divide this term, this term with this term, then you will be getting sine theta, from where you will be able to, sorry, you will be getting tan theta, from where you will be able to solve for theta, and you will get theta as tan inverse 2 kp divided by omega 0 square minus p square. So in this answer that we have obtained right now for a and theta, a is the amplitude of the oscillation, amplitude of the oscillation when it is driven by an external periodic force. A is equal to f0 divided by omega 0 square minus p square the whole square plus 4k square p square. The denominator has got a square root. So when you this is the amplitude of the oscillation. So when you look at this equation, you can see that this amplitude is a function of p, where p is the driving frequency, or the frequency of the external periodic force. P is the angular frequency. When you want to get the frequency, you will have to write it as p divided by 2 pi, because this p is a term which is appearing as a sine pt. So p has got the role of angular frequency. So when you want to get the frequency of oscillation, it will be p divided by 2 pi. So anyway, a depends on p. So in order to understand when resonance will take place, it means the amplitude will become maximum when this denominator is minimum. Okay, and in order to find when the denominator is minimum, since this is a function of p, it will be minimum when d by dp of this term, which is within the square bracket, when that term is differentiated with respect to p, and if that is 0, that is the condition for the denominator to be minimum. So when you do that, you will get this, differentiate this with respect to p and equate it to 0. So this is what you are going to get, from which you will be able to, for example here, this is just differentiation that I have done. You examine these terms and you will see that you got a 2 here, 2 here, and a 4 here, which we can cancel. This p and p you can cancel. So that will give you from this omega 0 square minus p square, you will be able to solve for p, and you will get p is equal to root of omega 0 square minus 2k square. So this means when the driving frequency is equal to this much, the amplitude of the oscillations will become maximum. So that situation is what we call resonance. That means under a particular driving frequency, when the amplitude of the oscillation becomes maximum, that phenomenon is referred to as resonance. In this equation, omega 0 is the natural frequency and k is the damping constant. Okay, and so if you plot the amplitude as a function of angular frequency of the driving force p, you will be getting a graph like this. Here we have taken the resonant frequency PR, and on the right hand side the driving frequency is increasing from PR, and on the left hand side driving frequency is decreasing from PR. So if you plot it, what you are able to see is that when p is equal to PR, the driving frequency equal to resonant frequency, the amplitude will become maximum. So this phenomenon is what we call resonance. That means under a particular driving frequency of the external force, the amplitude of the oscillation becomes maximum, and that phenomenon is what we call resonance. So if you observe it in detail, we will also be able to see that this is how it is going to look like in the event of no damping. And as damping increases, the amplitude will become lower, and in the event of high damping, the amplitude is lowest. And the on either side of the resonant frequency, the rate with which the amplitude is decreasing, it is actually symmetric. And this is also used to measure another important feature, which we call sharpness of resonance. It is actually the rate with which the amplitude is decreasing on either side of PR. That is what we call sharpness of resonance. Finally, we will look at three different frequencies that we have come across in this topic. First one is the natural frequency. It is represented as omega 0 by 2 pi. This is the frequency with which the system will oscillate if there is no damping and if there is no driving force. Whereas if there is low damping, we had earlier seen that the frequency will decrease and it will become root of omega 0 square minus k square. So in the event of damping, this will be the frequency, root of omega 0 square minus k square divided by 2 pi. And right now we have seen when there is resonance, which is taking place in the event of an external periodic driving force. In that case, there is something which we call resonant frequency, which is equal to root of omega 0 square minus 2k square divided by 2 pi.